Creating and altering indexes. So the primary purpose of an index is to speed up data retrieval. The tricky part, that of course lays on the shoulders of us database developers, is ensuring that our data access layers and our queries are actually using the indexes. So in this nugget, we're going to look at all the different kinds of indexes, how to create them, but also come up with a strategy to ensure that our indexes are used. So we'll start here with just a quick indexing overview to go over all the different indexes. We'll talk about statistics, we'll cover some guidelines, and we'll even talk about selectivity and density, a couple of important concepts to understand when you're thinking about creating an index. From there, we'll jump into the virtual nugget lab. We'll start by learning how to create all the different types of indexes. So clustered, non-clustered, included, filtered, and even the new column store index. Then we will take a real-world look at how to index a table. So I've got the perfect table. It has 1,000,000 records and nothing on it. So we'll look at the kinds of queries that are hitting this table to determine what kinds of indexes we should be creating. And then we'll employ all the guidelines we learned about in our overview to create a good indexing strategy and make sure that our data access layer uses our indexes and that those indexes are also doing their job and giving us speedy data retrieval. We'll finish this nugget up with a look at how to assess our indexes. Specifically, we'll look at statistics and how to view them and what they're all about. And we'll also look at something known as SARG. SARG is a made-up word constructed from the phrase search argument, and we need to ensure that our predicates are sargable. If they're not, then the query optimizer may do something else rather than use an index. So we'll look at what that's all about. Let's start with an overview. First thing I like to do when it comes to indexing, no matter what level of indexing we're talking about, is just define it. And it helps to give a real-world analogy with indexes, and we've got some good ones. Books, I love using books as an analogy. Anytime you use a book, especially a technical book, where you want to find a specific topic. Say you bought a SQL Server book, and you want to find out how Always On works. What are you going to do? You're going to scan that book page by page, chapter by chapter? No, you're going to look in the back of the book at the index to find the pages that topic is on, and that will allow you to take a shortcut and jump right to that. Same with libraries or bookstores. If you physically walk into a bookstore, are you going to start scanning shelf by shelf? No, you're probably going to go ask somebody or go to the computer, or if you're in a library, look at the index cards. An index in SQL Server works the same exact way. It's a physical structure known as a B tree, which stands for a balanced tree. When we create an index, we're going to specify a key. That is how the data is going to get stored inside of this index. And if we were to create a query that the query optimizer said, yep, this query can use this index, then SQL Server will have to simply make decisions along the way, left or right, every time it hits a node. If it chooses left, it's going to go down that path, ignore the whole right path then, and then it's going to make another decision, left or right, and then if it finds the data, it can pull it out. So it can take quite the shortcut to find our data. Now, these nodes are known as the root, the intermediate, and the leaf level of the index. And that's important because data is usually stored at the leaf level, and that is how it can pull the data out of the index rather than out of the data pages inside of the table. And this structure is going to act a little differently depending on the kind of index. For instance, a clustered index physically stores the data in order on disk by the key. And this is why you can only have one clustered index on a table, because that is going to be the actual data stored inside of the index. Non-clustered indexes is a separate structure that just simply stores the key values and pointers to the actual data. And so if you have a clustered index, that non-clustered index is just going to point to the leaf level nodes inside of the clustered index. If there is no clustered index on the table, the non-clustered index is just going to store pointers to the row IDs on the physical data pages stored on disk. Included indexes are non-clustered indexes that also store non-key columns at the leaf level of an index. And this is nice because we can create what's called a covered index. A covered index is one that if a query were to use, it means it can extract all the data out of the index rather than going to the data pages, because again, with an included index, those non-key columns are going to be stored at the leaf level. Filtered indexes, introduced in SQL Server 2008, allow us to create an index on a subset of data, and we accomplished that by putting a where clause inside of the index. It's great when you have a column that contains a set of known values. For instance, a region column. Say you have just a couple of regions, you have millions of records, and you have a region that is always queried on. You can easily create a filtered index for that region, and then any queries that hit that index for that region will be dramatically faster. Also good for sparse columns, because you can create a filtered index where a column is not null, and then you'll only be working with the data that has values. The column store index, introduced here in SQL Server 2012, is column-based storage. And to really understand how this works, most relational engines store their data horizontally on the data pages, which means at the record level. So field by field, column by column, the entire row is stored in a data page. With vertical storage, it just stores the column in that column's data. And why this matters for performance is because when SQL Server loads up data pages into memory, it could be loading a lot of unnecessary data at the data page to extract what it needs. With column-based, it's only loading that column's data. So we get an extremely efficient use of memory, and SQL Server has a lot less to do because it's loading only what it needs into memory. And there are other benefits as well to column-based storage, such as compression, much easier to compress this kind of data. But essentially, it's meant for the world of data warehousing, because if you put a column store index on your table, that table will become read-only. So those are our index types in SQL Server. We'll look at how to create each one of them when we get into the virtual Nugget Lab. Let's talk a little bit about statistics. Statistics are a lot like they sound. They're stat sheets for the data within the columns in our indexes. So anytime we create an index, stats are generated with it that store the distribution of data within that column. And what that allows the query optimizer to do is make better decisions, make better query plans, determine if what index is the right index to use, if any, when it comes time to retrieve the data. And I like to use the sports analogy. Professional sports, for instance, say you're a coach and you have a tough matchup this week. How are you going to determine what lineup to use? You're going to look at your stats. You're going to find out what players are hot, what's not, and come up with an optimal lineup based on your opponent. So without stats, coaches and the query optimizer would have a lot more work to do to figure out that optimal lineup. There's really not much for us to do in SQL Server when it comes to statistics. Leaving the defaults are generally a best practice, which are auto-create stats and auto-update stats. Letting SQL Server handle what's going to be fine for 99% of the databases out there. It's still good to know about them because it's another piece of the puzzle when it comes to troubleshooting. If you have a query that isn't utilizing an index and you really don't know why it should be, so your query plans aren't getting generated appropriately, then it's a place to look. It's absolutely a troubleshooting tool that you can use to see if your statistics are out of date. So at the most, you may manually update your statistics every now and then. And I'll show you when we get into the virtual Nugget Lab how you can determine if your statistics are out of date. Selectivity and density, a couple of other important concepts to know when creating your indexes. These are just measurements. Selectivity is a measurement of distinct key values, and density is a measurement of duplicate key values. So these are proportional to one another. They're both used to measure index weight and quality. Essentially how this works is, let's say that we have an employees table with 1,000 records in it, and we put an index on the date of birth column. Let's say any queries that hit that date of birth column will at most retrieve, say, 3 records. 3 records for a specific date of birth. That would mean our selectivity is 0.997 and our density is 0.003. That's good. That's really what you want to aim for when you're creating an index. You want indexes that are going to be highly selective. The queries that come at them are going to return small amounts of rows, and we put indexes on low density columns. That's going to result in the best usage of our index and the best performance for our queries. Just a couple of general guidelines here for indexing. Number 1, avoid over-indexing highly modified tables. Remember, the more indexes you have in a table, the worse insert, update, and delete performance will get, because SQL Server will do page splitting and it has to move data around, and it'll have to do that for all the indexes you have on your table. So remember that one. Also, use narrow index keys whenever possible. Exact numerics are the most efficient index keys. Integers, for instance, are going to be the best. Always put clustered indexes on your tables. That's another one. But also make sure that your clustered index is on a unique column, and a column that doesn't get updated. Also, make sure that you put non-clustered indexes on your foreign keys. That's a big one. And also ones that show up frequently in the where clause. And then don't forget about covering indexes for huge performance gains, so it doesn't have to go down to the data pages to get the data. It can use the index. All right, with that, why don't we head into the virtual Nugget Lab and create some indexes. Welcome back to the virtual Nugget Lab. Let's head into SQL Server Management Studio, where we have a new project, 16.indexes, inside of our solution. We're going to start here with just creating all the different kinds of indexes. And the first thing we're going to do here is set statistics IO on. This is a great way to see how much work SQL Server has to do to retrieve our data. And we're also going to turn on include actual execution plan. This will show us the query plan that was used to retrieve the data, so we can see what indexes, if any, were used. So we've got a table inside of Nugget Demo DB called Learner Nugget Activity that I reloaded. It has 1 million rows in it and nothing on it, no indexes at all. So I even took the clustered index off, so we have no clustered index or primary key or anything going on this table. And let's say we have a query that users are constantly submitting to our database that hits this table. And these queries are constantly going against our action time column and join two tables together, nuggets. So this query is going to pull out all the actions by nugget. So if we run this by itself, you can see that it takes about a second to run, but more so, we can see that SQL Server did a lot of work to get all of that data. That's a lot of logical reads, and we can cut that down with the appropriate indexing on this table. Also, if we look at our execution plan, we can see that we're doing a table scan. Table scans are bad. It's scanning everything in that table to pull back only that little bit of data that we want, which is anything with an action time greater than 2012. So 156,000 rows out of those 1 million, sure, it came back in pretty good time, but it still has to do a lot of work. And as data fills up in this table, this query could get slower and slower. So the first thing we need to do is plan a clustered index on our table. Now, you should always choose your clustered index wisely. In this case, we're using unique identifier, which isn't the greatest field, but this is all going to depend on your requirements, because we're saying that this table has so much data in it and constantly pumped into it on a daily basis that we needed this uniquely identify rows. But if this were a real design, we'd probably take the data warehousing route or the archiving route and leave the unique identifier there, pump all this data in there on a weekly basis or whatever we deem necessary, and then we could get away with a big int here in our transaction world, which would be much better for performance reasons. All right, so we'll stick with it for now, but let's just go ahead and create this clustered index. And now this isn't going to improve performance very much, because if we rerun our query, instead of a table scan, we're going to get a clustered index scan. So same amount of cost there, same amount of logical reads. So we really didn't do much by adding that. But what that did do is pave the way for our future non-clustered indexes. So now we're going to put a non-clustered index on our join here, which is going to be on our nugget table. So our nugget ID and our foreign key in this table. And then we're going to create a non-clustered index on action time, which is already seeing a lot of action from this query. So those are going to be the logical choices right off the bat. So let's do this. Let's execute this. This will create the non-clustered index on our foreign key. And now let's create another non-clustered index on our action time column. All right, so now we've got multiple indexes. Let's see what happens here if we run this query. Do we get any performance boosts? The answer is no. No. And it didn't even use our index that we created. Why? Anybody know why? Because the query optimizer deemed it more efficient to just work with our old plan, to just do the clustered index scan. And you can see here, it gives us a little advice. It says you should have you index the right field, but you should also include nugget ID in the action, because we're pulling back action and we could include nugget ID on this. It will absolutely give us a performance boost. So let's drop this index, drop index name on table name. We'll blow it away. Keep in mind, you can't alter indexes. You can only alter index properties. But if you're going to change structure of the index, then you need to drop it and recreate it. So that's what we're doing here. We're going to do that and create an included index. Same exact index, except we're including nugget ID action and even action position, which we're not using, but it won't hurt. And that way, if any queries come in that do use it, they'll still be able to take advantage of this index. So let's create that non-clustered index. And now let's head up and give this query another spin. So let's fire it up. If we look at messages, look at those reads plummet from 7,000 to 900. That's quite the gain. And if we look at our execution plan, it used our index. And the reason that was so efficient is because it used the index and only the index to pull the data off, since everything we needed from that query was pulled from the index since it was included and used. Let's move on to filtered indexes. So again, filtered indexes shine when you need a small subset of data. And here's a good example. Let's say that we added a new action called rate, where we could rate a nugget. And all of our other actions, there's a lot of them. There's an even distribution. But let's say that a lot of queries come in that just want to work with rate. So what we could do is put a filtered index on top of that column. So let's do that. Let's create a non-clustered filtered index called IXF rate action that takes learner ID, nugget ID, and the action, and then we're going to add a little where clause to it to say where the action equals rate. So it'll just store that small subset of data inside of the leaf level nodes of the index. Now, if we execute any queries that pull that data back, watch how super efficient this will be. 2 reads. And our execution plan used our rate action index there. So that's an extremely efficient way to work on small subsets of data. So if you have queries that are coming into your tables that only work with a specific set of data, then look at filtered indexes, because you can, as you can see, get some pretty big performance gains out of it. Now, the last one I want to show you here is column store. And we'll do a column store index versus a non-clustered index just to see the kinds of performance gains you can get. And we're going to do this against our Learner Activity Archive 2010 table. So let's say this is a read-only table, so it would be a good candidate to put a column store index on. So here's our query to test. We're going to do a group by on these 3 columns, which will result in our indexes covering those 3 columns as well. So let's first just get a baseline by running this test. So if we look here, we're doing 730 logical reads, and we're doing a full table scan because we do not even have a clustered index on this. So that was 730. So let's just mark that right here. 730 baseline. Now let's create a clustered index across those 3 grouped by fields, a non-clustered index. All right, so that looks good. Now let's run it again. Let's see if we've got any performance changes there. Yes, we've cut it almost in half. 420. So let's put that here, 420. And now let's delete that index just to make sure it doesn't use it. And now let's create our column store index on the same fields. Let's run that query. And the results are 124. Look at that difference. So that's a great way to test out column store indexes. Look at that performance gain. That is pretty unbelievable. And just to verify too, we can see that our execution plan used our column store index, and we can also see that our column store index is there. Now, before we move on, I also just want to say that the best real-world advice I could possibly give anybody is to do this kind of stuff. Test. Write your queries, create your indexes, and then test your queries. Look at their I/O for performance benchmarking. Look at the query plans to make sure that the indexes are actually getting used. And that's really the only real way you can ensure that your indexing strategy is going to work. All right, on to an index strategy. So this is pretty much everything that we were just doing, just at a different level. So our index strategy here is going to be choosing a clustered index. We saw how to do that and to choose one wisely. Index foreign keys, always a big deal. Discover the kinds of queries that will be hitting your database. Talk to your developers. Talk to your business intelligence users, your data analysts. Anybody that is going to be hitting this database with a query, talk to them. Find the common denominators between all those queries to come up with your indexing strategy. Then it's always best to create a small set of indexes to support the most critical and intensive queries to start. Then you can add more as you go, but just keep in mind, again, try not to over-index tables because that can cause problems. And finally, the last one is probably the most important of all. Reevaluate often. We've looked at DMVs and previous nuggets to discover missing and unused indexes. And really, indexes are a lot like an automobile or a house or a significant other. If you ignore them, they will get mad and make your life miserable. So revisit your indexes and give them a little TLC every now and then. So here's what we're going to do. We are going to create a bunch of indexes here that cover our Learner Nugget activity table. So I blew away all the existing indexes. I left our clustered index and our filtered index on because those are okay. But I blew away all of our other indexes. And let's say that we talked to our business intelligence developers. We talked to our application developers. We've talked to our data analysts and our business analysts. And we see that people that like to query this table like to query on the time, right? That's pretty common, putting date filters on reports and such to get snapshots of a specific date. We've got people that run queries just straight against this table to grab the number of events that occur, let's say by month in this case, by action. We've got other queries that join it to the nugget table to break out these events by nugget. And then we've got other folks that query it and join to the learner table and the nugget table to break these events out by learner and nugget to pull out, say, things like bookmarks, who's bookmarking what. And that should be good there. So we've got a multitude of queries. We can see the common denominator here is going to be action time with potentially action for text searches. So if we look here, we could say, well, obviously we've got a clustered index. We're going to employ our foreign key indexing. So that's what this will do for us here. We'll create a non-clustered index on both of our foreign keys separately. All right, so while that's going, we'll flip over here. Then to handle any date time searches, we're going to want to put a non-clustered index on our time. That's going to be a good one. That'll speed up any search that hits that. And then we'll also include Nugget ID, Learner ID, and action. We'll see anytime somebody queries against the time, they're going to pull back some kind of table so we can get a huge performance gain by covering the index. All right, so queries that come in will pull only data from the index. So we'll do that. We'll create that, and then we'll say to handle those text searches against action, we're also going to want to get an index going on our action column. But remember, this is actually a pretty low density column because there's just not a lot of unique values. We've got like 4 or 5 values across these millions of rows, and I'll show you that when we look at statistics how you can see that. But let's create this one anyway because it's better than a table scan. So don't let the fact that low density columns aren't good candidates, because it's still better than scanning the entire table. All right, so that's what we're going to employ there. Now let's turn statistics.io on just so we can see if we're getting some good results here. Let's run our first query, execute it, look at our messages here, and that's pretty good. That's pretty good. I think before we were up at like 7,000 some. So we've cut that down dramatically on this. And if we look at our execution plan, let's just turn that on here and re-execute it. We can see that we are using exactly what we would hope it would use, IX action time. That is our index right here that's on top of our action time that includes these other columns. So that's good news. Let's try another one, buy nugget. Let's see what this one does. Hit execute. If we look at our messages, same thing. We're way down there. That's very good, and even our logical reads against our nugget table is good. If we look at our execution plan, we are using the same thing. So that is also good because, again, that was more of a time search. So those were pretty much the same thing. Now this one's going to use action here. We're actually, our predicate here is going to include action. So this should actually use our text search index that we created. And if we execute it, first let's look at our reads. Good. Our reads look good. 844 reads, 120, 141 against our join tables. Those are good. And if we look at our execution plan, what do we get? IX actions. There it is. Perfect. So indexing is both an art and a science, but it's really just all about understanding the data access layer, and the kinds of queries people are submitting to your tables will help you employ the right indexing strategy. And if we look at our indexes here, we've got a good coverage because based on the queries coming in, we can handle text searches, we can handle date searches, and we have both of our foreign keys indexed, along with the clustered index, and then just for kicks here, we added that filtered index against that special action. Another thing we should talk about is SARGs. SARG stands for search arguments, and it's the idea that how we construct our predicates, our where clauses here, is going to have an adverse effect on query plans. In fact, one of the biggest things you can do to make your queries non-sargable is by using a function before your operator in your where clause. So, and that's because SQL Server, the query optimizer, is going to look at this data and it's going to say, hey, that's a year. That doesn't match the key inside of our index, so it's not going to do it. It's going to do a scan rather than a seek. Now, below is the same exact query. The only difference is that we're querying for the year 2012 by doing a greater than, less than against action time rather than using a function. So always do this whenever you can. Avoid doing this, and here's why. Let's highlight both of these and execute them. Go into messages. Here's the first query, 6,400 reads. Here's the second query, 634 reads. If we look at the execution plan, first plan is doing a scan. Second plan is doing a seek. You always want to do seeks. They're way better than scans because it's searching for the actual data. It's high selectivity versus low selectivity. And here we go. First one, 63% of the batch. Second one, 37% of the batch for the same query. So that's one of the big reasons there that you want to be careful when constructing your where clauses. The last thing I want to show you here is just a little bit on statistics. So you can run a DBCC show statistics, pass in a table and an index, and it'll give you all the good information you want to know about those statistics. And this same information, by the way, can be seen graphically. If you just head into the statistics node, here it is. So it's the same exact info if you right click and go to properties and you go to details that we're getting here from DBCC show stats. So anytime we create an index, it'll create the statistic associated with it with the same name. It'll also create system statistics. These are for fields that are not in our indexes but are still referenced in queries. It'll create statistics on the fly so the optimizer can use them to efficiently pull that data. In fact, I just ran a query that pulled back action position, about the only field we haven't used in our queries. And if we look at this, or our indexes I should say, we do not have action position in any of these. But if we look at this, we go to details and scroll over, check it out. It automatically created a statistic for this column. Let me just briefly go over the result sets here returned by DBCC show statistics. So the first one is just metadata about our statistics. The important one here is we can see when it was last updated. You can also see your average key length. You can see if if it's a string index, if it has a filter associated with it. The second one is the density, and this is going to be the important one for discovering how unique or how many duplicates are within a column. So it breaks it out. First, it shows it by itself, just using the index key, and then it breaks it out using comparing it with the clustered index key. So we can see we have a low density here, which is good. That means we have high selectivity. We have a high number of unique values against our nugget ID column. The last one then is just showing our data distribution stats. So this is essentially what our index looks like, what those ranges are, and what it's going to use to traverse the index. All right, now let's try one more here. Let's look at our actions. This one should be the opposite, and we can tell here that it has a high density, which means it has low selectivity, and that's because we just don't have a lot of values here for this field. We can also tell by looking at this that our key length is a lot wider than our previous index, and that's because it's a character index. So while this index may not be nearly as efficient as our previous one, it's still going to be a lot better than no index at all, right? Scans are almost always worse than seeks. In this CBT nugget, we learned how to create and alter indexes. We started off with an overview. We got familiar with all of our different index types. We talked about clustered, non-clustered, included, filtered, and column store indexes. We talked about statistics, saw what those are all about. We talked about selectivity and density, and we also covered some general indexing guidelines. Then we jumped here into the virtual nugget lab. We saw how to create all the different kinds of indexes. We saw how to employ an indexing strategy, and at the end here, we learned how to assess our indexes and look at statistics. I hope this has been informative for you, and I'd like to thank you for viewing.